Welcome to IT.Solution, your total network, system, firewall, and security partner.
Welcome back to The Explainer. Today, we're diving straight into ITN Module 6, and we're going to completely demystify Layer 2 of the OSI model. If you've ever sat there and wondered how the logical, purely digital world of software actually connects with the messy, physical world of cables and radio waves, well, you are in the exact right place. We're looking at the data link layer. It is basically the ultimate bridge. It translates software logic into hardware signals, making absolutely sure our data doesn't just, fall apart the second it hits the physical world. So let's kick this off with a pretty fundamental question. Just think about the sheer, mind-boggling scale of the internet for a second. We've got billions of devices connected all at once. How in the world do all those raw ones and zeros not just violently crash into each other in the total chaos of a busy network? How does raw data actually survive that journey across a physical copper wire or flying through the air? The answer is literally all in the invisible rules of Layer 2.
And here is our roadmap for today. First, we'll officially meet the data link layer. Then, we'll break down the LLC and MAC sublayers. Third, the anatomy of a frame. Fourth, Layer 2 MAC addressing. And finally, we'll wrap up with media access control methods.
Okay, Section 1. Meet the data link layer. Let's get a handle on exactly where this layer sits and the monumental task it's pulling off every single millisecond.
The big takeaway here is that Layer 2 sits perfectly sandwiched right between the network layer above it and the physical layer below it. It grabs IP packets, the stuff holding your emails, your web pages, your video streams, from the network layer, and it encapsulates them for safe physical transport. Whether your data is about to get blasted over a copper Ethernet cable at the office, a fiber optic link, or just your home Wi-Fi, Layer 2 preps it for that exact specific media. And crucially, it acts as a bouncer, doing error detection to reject any corrupted data that might have gotten scrambled along the way.
Moving on to Section 2, the LLC and MAC sublayers. This is where it gets cool, because unlike most other OSI layers, Layer 2 actually has a split personality. Think of these two sublayers working together like a highly efficient translator. Up top, you've got the LLC, or Logical Link Control. The LLC communicates up to the network software, figuring out if you're using IPv4 or IPv6, for instance. But down below that is the MAC, the Media Access Control sublayer. And the MAC talks down to the physical hardware. It handles the actual encapsulation of the data and dictates how your device physically accesses the media. So one side speaks fluent software and the other speaks hardware.
Because of this dual personality, your data goes on a really fascinating journey. Every time a packet travels across multiple networks, it experiences a bunch of media transitions. And at every single router hop, 4 exact things happen. The router accepts a frame from the incoming medium, it de-encapsulates it to peek at the IP packet inside, then it actually re-encapsulates that packet into a brand new frame built specifically for the next medium. And finally, it forwards it on. So the IP packet inside, that stays exactly the same. But the Layer 2 frame, it is constantly being destroyed and rebuilt at every stop.
All right, Section 3, anatomy of a frame. Because to move that data successfully hop to hop, the MAC sublayer has to package it right.
I always tell people to think of a data link frame literally just like a cardboard shipping box. When you ship something, you don't just hand the raw item to the delivery driver, right? You put it in a box, you slap a label on the front, and you tape up the back. While the data link layer does the exact same thing to ensure your data isn't just tossed out into the void. It meticulously adds a header to the front of the packet and a trailer to the back.
Let's actually look at what goes into that digital box. The header is your shipping label. It's got the source and destination addressing plus control info. Then in the middle, you have your actual data payload. But check out the trailer. This acts like a tamper-evident seal. It contains a frame check sequence, which runs a mathematical calculation called a cyclic redundancy check, or CRC. If the receiving device runs that same math and gets a different CRC number than what's stamped in the trailer, it knows the frame got corrupted in transit and it instantly drops it. Absolutely ruthless.
Section 4. Layer 2 MAC addressing. We just talked about the header having addresses, but these are not the IP addresses you're probably used to. Let's see how Layer 2 navigates the local link.
We are talking about the MAC address. This is a 48-bit physical address, usually written out as 12 hex digits, and it is physically burned into your device's network interface card. It's pure hardware. Now, your IP address defines your entire end-to-end global journey, but this MAC address, it is strictly local. It only exists to get your frame from one network card to the very next one on that specific shared network. And here is where the real magic happens. Say you're sending data to a web server halfway across the planet. Your device knows the server's IP address. But for the Layer 2 destination MAC address, it actually uses your router's default gateway MAC address. The router is literally the exit door from your local network. And remember what we said earlier? At every router hop, that old Layer 2 frame is stripped off and a new one is built. That means the source and destination MAC addresses are completely swapped out at every single hop, even though the IP addresses tucked safely inside never change.
And finally, Section 5, Media Access Control Methods. Let's look at the traffic cop duties of Layer 2, because when devices share media, we need hard rules to stop data collisions.
So first, we have to look at the environment itself. Half-duplex communication is basically a walkie-talkie. Only one person can press the button to speak at a time. If both try, the signals just cross and scramble. That's exactly how wireless LANs work. But full duplex, that's a modern phone call. Both sides can talk and listen simultaneously without any interference at all. Modern Ethernet LANs that use switches operate in full duplex. They don't even need complex rules to avoid collisions because physically, collisions just can't happen.
But for those half-duplex setups, we rely on contention-based access. There are two heavyweights here. Older Ethernet used CSMA/CD, collision detection. It actually allowed collisions to happen, noticed them after the fact, and then forced devices to wait a totally random amount of time before trying again. Kinda clunky, right? Today, Wi-Fi networks use CSMA/CA, collision avoidance. Before sending anything, your Wi-Fi device broadcasts exactly how long it needs to use the frequency. It's essentially reserving the airwaves and actively avoiding the collision before it even has a chance to happen.
Now, totally opposite to those contention methods where everyone's fighting for the mic, older controlled access systems use what's called deterministic access. Think of it like a strict traffic light. In legacy setups like Token Ring, an actual digital token was passed around in a circle. You could only transmit if you were holding the token. It gave every single node a scheduled, guaranteed turn to speak with zero risk of collisions.
So as we wrap up this explainer, I really want you to consider this. We almost never think about the data link layer. It operates entirely behind the scenes. And yet every text message, every 4K video stream, every email you send relies 100% on this microscopic traffic cop and translator. It's constantly packaging your data, navigating those local physical links, doing the math to check for errors, and actively preventing collisions. It's the only reason our complex digital world doesn't just evolve into total physical chaos. But here's a thought to leave you with. As we accelerate toward a future packed with billions of simultaneous IoT devices and quantum networks, are these legacy traffic rules going to hold up, or is Layer 2 fundamentally due for a massive revolution? Thanks for hanging out and exploring the mechanics of ITN Module 6 with me today. Keep learning, and I'll catch you in the next one.
Thank you for watching. See you in the next episode.